Hi, we'll talk about the optimality of Grover search. We know that the Grover search algorithm can search a marked element in order of square root of n queries, which means if you just look at the query complexity, then the runtime, um, I should say that the query complexity, number of queries are less than or equal to some constant times square root of n. Now, the question is, can we do better than this? And it turns out that there is a theorem called the BBBV theorem, says that there cannot be a quantum search algorithm that can do better than this. So the best algorithm will require um, omega or square root of n uh, no fewer than no omega square root of n queries. So BBBV stands for Bennett, Brazard, Bernstein, and Waziran. Right. So that means that we also have c square root of n less than queries, and therefore the Grover search algorithm is optimal. Right. But how do we prove this? So I won't prove the entire thing, but I'll just give you the proof idea. So proof of optimality of the Grover search. And we'll assume that there is only one marked element for simplicity, and O of X is the oracle or the black box that we apply. And so the proof idea is the following. So consider the state where you start with some initial state psi and apply the oracle followed by some unitary u1, then again apply the oracle, then u2, and this sequence is applied k times. And consider another state psi k where the oracle isn't applied. So this is an arbitrary initial state. And then this is a sequence where the oracle is applied, followed by some unitary, and another state that gets created when the oracle is not applied, right? And consider the quantity dk, which is sum over all possible x, psi k x minus psi k square. So this is a measure of the deviation of these two states over all possible marked elements. And so the idea is the following, that if we can show that dk is small, if dk is slow growing function or small, then all the phi kx are roughly the same, and therefore it is not possible to distinguish between a marked state and any other state with high probability. And therefore, it is not possible to correctly identify a particular X with high probability. Okay, so um, the proof consists of bounding decay in both upper and lower bounding in decay. So recall that decay is sort of the deviation between um, if the oracle is applied after each successive unitary, and U1, U2, UK can be arbitrary unitaries, and the if the oracle isn't applied. And we want to show that decay. So one is that, so proof has shows two inequalities. So inequality A shows that decay is relatively slow growing. So it grows as order of k square. In fact, they show that dk is less than or equal to 4k square. And the second part, which is um, more important, which says that if I have to have a high probability of detecting a particular marked element, which means let's assume that this probability is greater than half to identify a particular marked element, if we apply the oracle, has to be sufficiently high, and let's say that it's greater than half, then dk is at least c times n, right? So if you have to have a high probability of success for a particular marked element, given that the oracle is applied, and let's say that probability is greater than half, then dk has to um, be at least c times n. And using these two inequalities, we get Cn less than dk less than 4k square. So k is greater than Cn over 4, which proves the, lower bound for the Grover search. Now, this is quite disappointing because most of the NP-complete problems can be thought of as search problems over a large space. And so with this particular strategy that we have for the Grover search, you can get at most a quadratic speed up. And as you know, there does not exist any polynomial time algorithm for NP-complete problems. So the Grover search ideas or similar ideas will not quite work in solving those NP-complete problems. Either way, what we have shown is not a complete proof, but these are the main ideas. And then there are several inequalities that we have to work with, like Cauchy-Schwarz and so on. The details will be in any standard book, but the ideas are to bound this quantity d sub k, where one is where the successive oracles are applied, and other where oracles are not applied. And then this quantity doesn't grow that much. And if we have to find a high probability of success, then the quantity has to be at least of uh, order n. And then we combine these two inequalities to say that k has to be at least square root of n, right? So that's the idea.